Okay, thank you very much, Lars. It's been a pleasure to talk with quite a variety of you, as always, here at KITP. So yes, I am indeed going to talk about black holes and what we can potentially learn about them in the next few years from gravitational wave observations. So black holes, as you know, are great favorites of the general public as well as scientists. The general public, because black holes are insatiable death machines, and scientists, because black holes are insatiable death machines, that also happen to probe an extreme realm of physical phenomena, which means that by studying black holes, it is possible to get insight into some very fundamental aspects of physics. In addition, we have learned gradually over the last couple of decades or more that black holes have a key role in affecting even things as large as galaxies, so they have a great deal of astrophysical interest as well. Now, to fully evaluate the effect of black holes, it's important to bring together as many observational techniques as possible. Something that's going to be coming up, as I will describe to you, in the next few years involves gravitational waves. So these are ripples in space-time. These are going to yield new observational windows into some of the many faces of black holes. And we're talking here about seeing some of the most dynamical events in the universe. In-spiraling and merging black holes, supernovae, echoes from the very early universe. In addition, these are expected to be able to tell us with greater precision than other methods could apply about gravity in its very strongest realm. So something we cannot currently test. So these are reasons why gravitational waves are greatly interesting to us. However, although gravitational waves, or gravitational radiation, I'll sometimes interchange the terms, this has radiation-like qualities. There are significant differences between gravitational radiation and our ordinary electromagnetic radiation, one of the most obvious being that gravitational waves are really, really weak. So to give you an idea of what I mean by this, think about electromagnetic radiation. There are sources strong enough, you don't have to know anything about them to see them. You don't need to know about nuclear fusion in order to detect the sun. But in contrast, gravitational waves have not yet been directly detected. And as a result, when they are detected, it'll be necessary to use sophisticated statistical techniques, matching templates of expected behavior against the data in order to see the events at all, and then to, of course, interpret them in an astrophysical context. So in this talk, what I'm going to do is I'm going to begin by discussing a little bit about black holes, sort of the basic issues of what they are, at least what they're expected to be, why we think they exist. I'll then talk about gravity's ripples in space-time, what could produce them, how would we detect them, and importantly, what we are going to be able to learn from them. And I'm going to post, as I go along, a list of open questions that I think may be addressable using gravitational wave observations within the next few years. Now, something else that I want to emphasize here, because I know we do have a number of biologists in the audience, is that in contrast to something like biology, where direct laboratory experiments obviously provide a huge amount of information, astronomy is largely a look but don't touch science. Now, for the good of humanity, this is probably just as well. Having black holes in a laboratory might have negative side effects. But it does mean that it's going to be necessary for us to put together all possible observations, looking at things in many ways, like the blind man and the elephant, in order to put together our full picture. And this is why a new window like gravitational waves is going to be particularly important. So with that introduction, let's talk a little bit about black holes. Now, it is sort of a standard thing to do to draw back the history of black holes all the way to 1784. Now, this is a bit of a stretch, but not terribly so. There was a gentleman in 1784 named John Michell. And John Michell was a classic 18th century polymath. He was an astronomer, mathematician, physicist, and clergyman. And he used his knowledge that you have the speed of light, which is not infinite. So c equals the speed of light. So this is fast. This is about 300,000 kilometers per second, but it's not infinite. And knowing that, he also was able to use the Newtonian theory of gravity and theories of motion, which had been published about a century earlier, to note that if you had some object, which, as physicists always do, we'll consider to be a sphere, and let's suppose this radius of the object is the following, where m equals the mass of the object, g equals Newton's constant, and we'll give you a value for this. This is approximately 3 kilometers times the mass in units of a solar mass. The circle dot is what we use for the sun. And so m sun is about 2 times 10 to the 33 grams. So this is the mass of the sun. So if you had an object that had this radius for a given mass, then what Mitchell suggested is that it might actually be invisible. It could be dark. And the reason it would be dark...
For the velocity of light, I mean, what was wrong?
Sorry, how...
Did Mitchell have a number for the velocity?
He did. It wasn't a very precise one. However, almost a century earlier, the Danish astronomer Ole Rømer had looked at the eclipses from Jupiter's moons. And very good. Okay, so not a great value, but he had some value. So at this radius, the escape speed from such an object would in fact be the speed of light. So anything more compact that would be larger than the speed of light. And so he reasoned that such objects, possibly the most massive in the universe, could actually be completely dark. However, compared to our current view of black holes, Mitchell's dark stars were comparatively benign. So, for example, he would have thought, had he known about rockets, that it would have been possible to land on one of his dark stars, have a nice little picnic perhaps, take some samples for later analysis, and then gradually push off. So that even though the escape speed is greater than the speed of light, you can just push away in the same way that if I wish to ascend a flight of stairs, I do not need to take one almighty leap to get to the landing. I can push myself up gradually. So in the same way, he would have imagined that light would struggle off from the surface, gradually losing speed until it was brought back down. However, in Einstein's general relativity, which is our current best theory of gravity, this is not the case. As a matter of fact, the stars here aren't stars in the usual sense at all. So rather than, the Earth or the sun or pretty much any other object you can name, black holes do not have surfaces. Instead, they have points of no return, which are called event horizons. Such that if you go inside the event horizon, which by coincidence in the normally used system of coordinates has exactly this value for a non-spinning black hole, you wouldn't be able to make any outward progress at all. So once in, you're doomed completely. So that's a bit of an issue. What it means is that if something falls into a black hole, then you're never going to see it again. For practical astronomical purposes, although the firewalls 2-week discussion that's having its time here is going to discuss a little bit more about whether you can get the information. But for astronomical purposes, you drop something and it's gone. Now this obviously means that it's a bit of a challenge to look out into the universe and identify black holes. It's not the sort of thing which most other objects are, where you can see something shining. A black hole by itself in a vacuum is just plain dark. However, people have, throughout the decades, managed to come up with a variety of candidates. And the easiest way to do this is to see the effect that your black hole has on other things around it. So as an example, if you have gas which spirals into the black hole, it's moving faster when it's closer to the hole. So in some sense, you have a friction which can release a huge amount of energy. And indeed, this is an incredibly efficient way of generating energy. Between about 10 and possibly up to 60 times as efficient as nuclear fusion is. And indeed, these are thought to power some of the brightest things in the universe, things like quasars. There's an even better example in our own galactic center. If you look towards our galactic center and you wait for roughly 20 years, which people have, you can actually, with remarkable observational techniques, see the motions of a variety of the stars nearest our galactic center. So I'll have my little X here as sort of a point of orbit. And so we can see stars that are going around here and coming around here and so on in various curves. And with enough of this, you can actually figure out that here in this X happens to be something that has a fair amount of mass, but that you really can't see very well. So in particular, what you see in the center of our galaxy in this little X is something that has a mass which is something like 4 million times the mass of our sun. And the radius is less than or about the radius of the solar system out to, let's say, Pluto's orbit. Well, OK, and in addition, it's dim. So we're talking about something where the luminosity is, less than or on average or about the luminosity of our sun. So you've got something 4 million times the mass of our sun, which is basically as dim as our sun, if not dimmer sometimes. OK, so what does this mean? Well, it's a possibility, of course, that you've got a black hole there, but you have to be able to rule out other options. And just to give you an idea of the kind of occasionally indirect way that we have to do our reasoning, you might first imagine that with this huge amount of stuff packed into this relatively small volume near the galactic center, that the only way that you could pack anything in would be a black hole. But actually, you have to be careful because space is ridiculously vast. And indeed, if you were to just place copies of the sun inside this volume, you could fit nearly 1 trillion of them there. To put it another way, if you were to put in 4 million solar masses and get the radius out, it would be about a 500th of this radius. So you're still a long way from being able to say very, very directly that you have, your single object. You could argue that if there actually were 4 million suns in this vicinity, then it would be really bright. And it would things would be running into each other all the time. And this would be correct. But there are other things out there. Yes?
Do you think about the spin of a black hole?
This is controversial. There have been some arguments that some observations suggest that it's spinning like half maximally. But the arguments that have gone into that, I think, are not definitive. So in particular, you see a quasi-periodic oscillation in the infrared, which has been interpreted as the result of the spin. But I think that whether this is truly quasi-periodic or just the random stuff that is done by accreting matter is unknown. Yeah. So you would like to argue that stuff will run into itself or be glowing really hot. But as a matter of fact, there's a lot of things out there in the zoo of astronomical objects. For example, something that we will discuss more later, neutron stars, very small things like the size of a city, very dim, and weighing as much as a star, so they would be just fine. They would be totally dim, you'd never see them, and they wouldn't run into each other. So you have to actually have an argument that's a little bit stronger than this and a bit more general as well. And so the way you do that is you actually have to go back to the nature of gravity itself. So as a reminder, our sun is a solitary star. There are a few things orbiting the sun that we are particular to, but they basically just follow along. So the sun is nice and stable as it moves along in the galaxy. As you may know, however, there are quite a few cases in which you have a pair of stars orbiting each other. Well, the brightest star in the night sky, Sirius, has a companion, and so they can make a nice little elliptical orbit. Well, we're talking about a lot of objects here, and you might imagine that you can generalize this and suppose that there would be some nice kind of stable orbit. But as a matter of fact, what you can show is that if you have 3 or more objects of comparable mass orbiting around each other, then even if it starts in a regular way, the perturbations cause it to go kind of crazier and crazier, and eventually it's going to get flung out. Thank you. So what this actually says is that if you were to try to pack millions of things into a volume as small as this, you would find that in a comparatively paltry few thousand years, they would be flinging themselves out like crazy. And given that the galaxy is many billions of years old, this is simply not a good argument. So this is one of the reasons why we believe that black holes actually do exist. However, even though that's the case, currently we still have very little information about the nature of strong gravity.
Sorry, you said so the argument was that the stability of that structure
Yes.
was not in agreement with the idea that there could be some kind of orbiting structures there.
Right, so having one object is perfectly stable,
Right.
but having millions is not going to happen.
But the observation that gave rise to this calculation was 20 years, just 20 years. Is that long enough to rule out, to have a statement on the stability of these structures?
Oh, sorry, let me clarify that. So the 20 years by itself is not enough to clarify the stability. The comparison is knowing that if you actually had millions of things within this small volume, they would interact with each other and throw each other out on a timescale of thousands of years. In other words, a millionth of the actual age of the system. So compared to the age of the system, it's totally unstable. Yeah. Okay. So we'd like to be able to use our understanding of black holes or observations in order to say things about very strong gravity. Now, let me explain why this is briefly, and we'll return to this in a little bit. If you think about our fundamental theories of physics and the basic forces that govern us, gravity is by far the least understood. It's the one that, it works, our current theory works fine in the observations we've done, but it's not been possible to really put it to the test. A useful ratio to think about in this case is actually kind of related to this. So we'll do it in, say, we'd like to know what is the value of g times m over r times c squared for various objects in which we have been able to test our theory of gravity, Einstein's general theory of relativity. So at the surface of the Earth, we're talking about something that is about 10 to the minus 9. If we're talking about, say, at the limb of the sun, this is maybe a few times 10 to the minus 6. So tiny values. And indeed, this means that the extreme aspects of black holes, things like their event horizons, are not anywhere close to being tested by these observations. So for a black hole, as we saw from here, we're talking about on the order of 1. So the study of black holes is something that we really need in order to understand strong gravity to push our theories to the limit as much as we can. And people have done this electromagnetically. In fact, all wavelengths of electromagnetic light have contributed. Radio waves, visible light, X-rays, gamma rays. There's a tremendous amount of progress made, a lot by people in this room, in fact. But if we wish to get unambiguous signals from really close to where the gravity is maximal, gravitational waves are going to play a major role. Now, to give you an idea of gravitational waves and sort of define them and go on with them, let's use a classic analogy. So first I'll start out with mentioning that Einstein and others came up with the understanding that space and time, which are separate in our everyday experience, are actually part of one quantity called space-time. This has lots of bizarre consequences. For example, when you have very fast relative motion or large differences in how deep you are in a gravitational potential well, then the duration of an event or the time between events can seem to be quite different from each other in those two different frames. So if you think about space-time as a rubber sheet, kind of a strange picture, but you imagine a rubber sheet, and you imagine first that you have no massive things around. So it's a nice, just flat rubber sheet out there, and you take a light thing like a ping pong ball and you roll it, and it goes straight. Just in the same way that we know from Newton's laws that if no force operates on something, that's what it's going to do. Go nice, straight, constant speed. On the other hand, if you take a bowling ball, something heavy, and put it on the rubber sheet, you have a dent that is produced. And if you were to take your light thing, your ping pong ball, and roll it past, it would bend. It would follow the curve. You can then say, well, what if you have two bowling balls? You place two bowling balls in this rubber sheet and start moving them around each other. These will generate ripples in the rubber sheet. Those ripples will take away energy, and the bowling balls will gradually spiral towards each other and will eventually hit. So the analogy here is that gravitational waves are these ripples in space-time. Now, what it means in practice is that if gravitational waves were to go past you, then what they would do is they would stretch and shrink you until they have eventually gone all the way past. this is what we'd like to measure. And indeed, when you're talking about, say, two black holes coming together close to that source, the gravitational waves are huge in their amplitude. But where we are, fortunately very far away from black holes spiraling into each other, the gravitational wave amplitude is tiny. We can't make them in the laboratory. So it's not possible to have a spinning lump of something or other which is producing gravitational waves, although there does exist a model of such a thing at Caltech. In addition, the nature of gravitational waves and gravity itself are such that not only do you have kind of an expected weakness, but there are only certain types of sources that can generate gravitational waves. So in terms of the expected weakness, just as something we don't really think about but is still actually kind of remarkable, you know well that a refrigerator magnet can hold up a paperclip against the entire gravity of the Earth. So pretty clearly the electromagnetic force is boss in that stage, at that level. Well, what are the things that can generate gravitational waves? You might imagine that since we're talking about rippling space-time, that a violent event, like the explosion of a star, the collapse of the core of that star to a black hole, could produce a huge amount of rippling that would be delightfully measurable by scientists. But that doesn't quite work. You may remember that Newton showed, good old Newtonian gravity, if you are outside a spherical collection of matter, you experience the same gravitational attraction no matter how it's distributed, as long as it's spherical and inside you. So it's like everything is concentrated in a point at the center. Now, this is something that is also true if you go to general relativity. What this means, though, is that if you are very, very far away from something like an exploding star, if that star were to explode spherically, and you were to close your eyes and measure the gravity that way, you'd see no difference whatsoever with the explosion, none. Similarly, even the collapse to a black hole, if it happens spherically, is not going to produce any gravitational waves. So there's a limit. Another one happens to be that if you have an object that is spinning around an axis and it is symmetric around that axis, no gravitational waves. So there are only a relatively small number of categories of events that can theoretically produce your gravitational waves. And
by that, do you mean measurable gravitational waves? Because you're producing gravitational waves right now. They're hard for me to measure.
It's true. I mean, although I should point out that although I've been eating very well here, I'm not quite a sphere.
Exactly. That's why.
So my non-spherically symmetric, non-axis symmetric motion is generating gravitational waves of a negligible amplitude. But in principle, even something that has completely spherically symmetric motion emits zero gravitational waves. So any deviations is what you need. So what are the categories of gravitational wave sources? So the official four that have been listed by the groups that want to detect these things are binaries. And this could be anything, but we'll talk about, say, two black holes orbiting around each other and gradually spiraling in. We have continuous wave. And the issue here is, imagine you have, say, a star that has a lump on one side and it's spinning around, and the lump is moving in a non-axis symmetric way, so it's always offset from the center. The difference here is that binaries will spiral in and get higher in frequency and amplitude. This can go on for a while, one presumes. A burst source, which is sort of we give up categorizing this thing. It's some event that generates gravitational waves, but in a way that we can't easily predict. For example, if you have the explosion of a star in a supernova, there's sort of turbulence or whatever in the center that might generate these waves. And the last are the so-called stochastic sources, which is really a superposition of a lot of sources which are individually, they can't be resolved from each other. And the sexiest by far of this category would be gravitational waves from the very early universe, something that would gladden the hearts of cosmologists. But let's think in particular about binaries to give you an idea of the weakness of these gravitational waves. So what I'm going to do here is I'm going to write up the strain that you would get. So this is the fractional amount of stretching and shrinking. So the fractional amount by which a distance could be changed for a particular type of binary. So H is what you have here. And I'll explain some of these things as I go. Okay, so tiny number, eek. So this is scaling as if you have two neutron stars orbiting around each other, approximately. We'll get to those in just a minute. With an orbital period of 10 milliseconds, so almost ready to smack each other. And then astronomers will recognize this as 100 megaparsecs. So this is the kind of distance where the next generation of ground-based detectors would be able to see it probably fairly straightforwardly. But yikes, it's ridiculous. Essentially what this means is if this were to go past the Earth, then the Earth's diameter would be stretching and shrinking by a distance that was less than the size of an atomic nucleus. So you need some pretty amazing ways to detect these. And they haven't been detected directly yet. So you would be very justified indeed in asking whether we have good reason to believe that gravitational waves exist at all. So is there some way that we can say, without direct detection, that yes, we're confident that they exist in the way that is predicted with general relativity, Einstein's theory? And the answer is yes, and it has to do with neutron stars. I mentioned these a couple times already, and in particular, so-called pulsars. So I'll give you sort of the facts here, then give you a little bit of history. So the masses that had been seen for these go between 1.25 and 2 times the mass of our sun. There might be ones that are heavier, but we haven't seen them yet. The radius is comparatively uncertain, somewhere between 10 and 15 kilometers. But notice this incredibly small size compared to the mass. So these are actually pretty strongly gravitating objects in their own. They're so tiny, in fact, that although their existence was proposed in 1932, most people had more or less given up on the idea of ever seeing them. They're so tiny by astronomical standards. I mean, here's where the range of scales in astronomy gets ludicrous. So one of these guys at a typical distance, the angular size would be similar to what you would have for a virus on the moon. So you're not going to be resolving it. And as far as the properties of these that might make them visible, well, there were some guesses, one of which turned out to be right, but most people didn't really think this was going to happen. But then, in 1967, an Irish graduate student by the name of Jocelyn Bell, who was working at Cambridge University in England and actually looking for and trying to characterize sources that turn out to be powered by supermassive black holes, made a fantastic serendipitous discovery. What she noticed with the radio array, where she did all of the electrical wiring over multiple acres of things, it looks like a bunch of clotheslines hanging the electrical stuff. She discovered very, very periodic radio sources, ridiculously so, far more periodic than had ever been seen in astronomy before. In the first case, every 1 1/3 seconds, there'd be a nice little blip. In fact, these were so regular that initially, she and some others contemplated the possibility that these were signals being generated by an alien species. Now, all of us know what it's like to be in graduate school, and so you may appreciate that, at least according to one story. Bell's first reaction upon thinking that it might be an alien race was, why did they have to contact me now when I was finishing my thesis? In any case, this became what is arguably the most important and impressive appendix to a doctoral thesis of all time. Now, these guys, in addition to having this remarkable mass and radius, where, by the way, if you were to take a spoonful from the center of a neutron star, it would weigh more than all 7 billion people on Earth put together. So this is an unusual state of matter, to put it mildly. In addition, the spin periods can be incredibly tiny. So they can be much larger, but they are greater than or about 1.4 milliseconds. So effectively what you've got here is a stellar mass, city-sized thing spinning around faster than a blender. Now, in addition, these things have magnetic fields. Magnetic fields that put anything on Earth or in laboratories to shame. You know, the weak ones would have a magnetic field 1 billion times that of the Earth at its magnetic pole. But this does cause them to spin down, but only very, very gradually. Indeed, if you were to take the steadiest of these guys, it would take many billions of years for it to spin down enough to double its current period. So as a result, in addition to being fascinating objects in their own right, pulsars are phenomenal probes of other aspects of the universe. As just one example unrelated to our current topic, the very first planets discovered outside our solar system were discovered around a pulsar. However, for our story, the relevance has to do with how pulsars were used in order to detect the indirect effects of gravitational radiation for the very first time. So the story is that in 1974, a young professor at the University of Massachusetts at Amherst named Joseph Taylor and his graduate student Russell Halse managed to discover a pulsar that was in a binary system with another neutron star. The reason this is important is, remember, we're talking about very tiny things, on the order of 10 kilometers. And at the separation of 1 million kilometers that these things were, this is a physicist's dream. They actually act like point particles. So you do not have to worry about any complications. And people were therefore able to use Taylor's very careful timing over many, many years to show that, in fact, the system was spiraling in at the rate predicted with general relativity to a part in 1,000. And for this discovery, both Taylor and Halse were justifiably awarded the 1993 Nobel Prize in Physics. Now, there is a bit of a backstory about this detection that was told to me by a fellow named David Halfand. He is currently the president of Quest University in Canada. For many years was a professor at Columbia University. Well, in the early to mid-1970s, he was also a graduate student of Joe Taylor at the University of Massachusetts. And Taylor sent him down to Puerto Rico to the huge 300-meter diameter Arecibo radio telescope to try to look for a pulsar in a binary, with the thought that you might be able to do this type of timing. So Halfand went, and he did his best, but he wasn't able to detect such a system and came back. Sometime later, another opportunity arose, and Taylor said, David, what do you think? You want to go down and do this observation again? And Halfand said, look, no, I don't. I mean, look, the odds of finding anything are slim. Besides, the food's terrible. And Taylor said, no problem, I'll send Russell. So I think the lesson here is that it's important to be able to appreciate their pulsars, at least their food. So we are, in fact, confident that gravitational waves exist, but we haven't seen them directly yet. And in fact, it is the direct detection where you are able to see the stretching and shrinking, which is going to give us the best information possible regarding strong gravity and the role of black holes in the universe. So let me now discuss a little bit about ways that you might be able to detect gravitational waves. And one thing I'll mention here, I'll put up 4 different methods. Remarkably, 3 of the 4 have an excellent shot of paying out in detecting gravitational waves within the next, say, 5 to 10 years. So there's kind of a good synchronicity here in that sense. So the thing to think about is, I mentioned that gravitational waves stretch and shrink things as they go by, but they do so in a particular and a special way. It's useful to kind of go back to electromagnetic waves. And remember that these are transverse waves. So if you have a wave which is propagating this direction, then you can have polarizations in the 2 perpendicular directions. And if you think about, say, the direction of the electric field, then a given wave is some combination, maybe time varying, of up, down, and left, right. With gravitational waves, in fact, it's a different situation, but they are also transverse. And if you were to imagine some ring of particles, which was in the way as the gravitational waves went by, then what you would find is that this ring of particles, in the same way that you have up, down, left, right, would either do the sort of plus configuration, so it would stretch and shrink in this way, or 45 degrees rotated. The reason that is relevant is if you were to imagine having some device which could measure distances, and let's suppose that they're in an L, and suppose that you have, this is the rest configuration. You can imagine that this is going to be contracted at the same time that this is extended. And then in the next cycle, this could be extended while this is contracted. So indeed, one of the ways that people have talked about finding gravitational waves is to take something that can measure distances very, very precisely. And the way that groups in the United States, Germany, Italy, Japan, coming up to India, have been thinking about this is by a laser interferometer. So essentially, you have a laser which sends a pulse to a mirror on each end, and then the light comes back after actually quite a few trips in the middle, and manages to interfere. So you have just the standard light interference. This is something which is being developed more and more as a technological technique. There have been a gradual improvement over the last, or really 20 plus years in this. And it seems very likely that this is going to be detected by 2020. So I'll put up here in terms of my methods, since I'm going to be setting these up. So we have our method, the frequency range. So what is the frequency of the gravitational waves that you'd be able to see with this method? What are the types of sources? And when is it likely to make a detection? So if we talk about this first one, these are actually on the ground. And there are technical limitations, which mean that it's actually necessary to look at pretty high frequencies. Going to lower frequencies, you start having worry about ground movement and things like this. So this is going to be ground-based. The frequency is somewhere on the order of 10 to 2,000 hertz, so really fast. Here we're talking about neutron stars and black holes primarily. And as far as when, I'll say it'll be earlier than 2020. Could be considerably earlier. Probably not earlier than 2016. That would take considerable luck. But the various teams are working hard on this, and it's really impressive to see their progress.
It's usually the case that the inequality is written the other way, so it's interesting.
Greater than 2020?
No, just that when people state when something happening, it's usually greater than something.
Ah, yes. Yes.
So you're stating a tremendous amount of confidence in your tax dollars.
I am. Of course, it's not my head on the chopping block if it turns out to be an inequality in the wrong direction. But I think there's good evidence that they're making progress. And so, yeah, let's say less than 2020. This same principle can be used with a different configuration. You can imagine putting these in like an equilateral triangle in space. So there you don't have ground motions to worry about. And if you are able to extend this out maybe to millions of kilometers, so no, you don't have an actual pipe thing with a million kilometers. We're talking about free-flying spacecraft sending lasers back and forth.
Is this called LIDA? L-I-D?
This used to be called LISA. This would be LIGO and Virgo and Cagra. And this would be LISA or ELISA or NGO or whatever it is they are calling these days. So we're not exactly clear. One reason is that this is going to be a lower frequency because it's much farther apart. The sources, I will write SMBH for supermassive black hole. Kind of gives you a cartoon feel to how powerful these things are. And so we're talking about maybe 10 to the 6 to 10 to the 7 solar masses. So sort of in the low end, as it turns out, of black holes that are in the centers of galaxies. I'll get to that in a bit. Now, when? Well, depends on whether it's funded. So this, like many space-based missions, has had all sorts of reverses and back and forth. So we can hope.
Are two supermassive black holes orbiting each other, or what?
They would be, yes. In fact, one of the things I'll get to a bit later is it turns out that most big galaxies have supermassive black holes in their centers. And if the galaxies collide, then the black holes can spiral towards each other. Something else I'll describe in just a bit here. Pulsars, once again, can come to the rescue and actually allow you to detect frequencies that are even a bit lower, 10 to the minus 6 hertz. So the issue here is, remember, these pulsars are spectacularly good clocks. So suppose you're able to look at a whole bunch of pulsars in our galaxy. The ones farther away would be too weak for us. And you're timing these very, very accurately. When does each blip arrive? Now, it's actually more complicated than it sounds, because the Earth is moving, and not just in a simple orbit either, but perturbed by the other planets. The sun is getting pulled around by Jupiter and Saturn, for example. We also have the pulsar itself might be moving, and so on. But people have managed, nonetheless, to be able to time some of these pulsars so well that they can accurately predict the arrival time of a pulse for the very best pulsars to 40 nanoseconds. So using this and understanding that if a gravitational wave were actually to come by and kind of pull and push the pulsar and the Earth away from each other, this can cause differences in timing that can actually show up in that case. And then the last one has to do with the very early universe. Well, of course, very early depends what you mean. It turns out, as you may... let's do that, yeah. So these are going to be somewhat more massive ones, so tend to be 8 to 10 solar masses. And it's a question of how lucky we are. But it is entirely possible that these are going to start having detections within a few years.
Lucky for what reason?
Lucky in the sense that the background here, which I was mentioning before, is you have galaxies in the universe that contain supermassive black holes. And these will sometimes collide with each other, and the black holes can spiral in and eventually merge. The question is, how often do they do that? And there are considerable uncertainties. Indeed, flipping that around, and sort of leading into one of my conclusions ultimately, is that the gravitational wave observations that you make, assuming you do have these detections, are going to be able to resolve an area of a lot of current uncertainty. Then the last one that I'll mention has to do with the cosmic microwave background. So as you know, the universe began with a Big Bang. I think there's a TV show about that, unfortunately. And it expanded, it cooled, and then about 380,000 years after the Big Bang, it became transparent. And so the light we see from that is a faithful record of the universe at that age. There are all sorts of details in the cosmic microwave background that have been processed in order to learn a tremendous amount about our universe. One of the things that has not yet been seen, but where there are largely ground-based instruments that are going to be pushing hard on this, has to do with aspects of the polarization. So if you look at the polarization of the cosmic microwave background, there's a particular type which can only come from gravitational waves. And the nice thing about that is that it would be able to give you information about the universe at a ludicrously early time. So first of all, we'll have our ludicrously tiny frequency, right? And the universe is less than 10 to the minus 33 seconds old. Yeah?
Well, unfortunately, the statement that it can only come from gravitational waves is not quite right, because it actually can be generated from lensing.
I'm thinking here about the low frequency ones. So the lensing, which already has been detected, is at a much smaller angle. So I'm thinking mainly about the low L, which is something that is only going to be produced at significant amplitude by gravitational waves. And here again, we're talking about a few years, assuming that the detectors are, in fact, as sensitive as expected, and assuming that the standard model of cosmology is correct. So not seeing these might be a sign that it isn't.
Well, there's another assumption, which is that we understand something about the inflationary period, which is a massive uncertainty.
It's true. So if you look currently at the spectral index and its deviation from 1, and you say, what is sort of your best guess, assuming no strangeness of the potential, then you should be able to see this in a few years. However, it is, as you say, possible to dial that potential pretty much as you want. And therefore, the best thing I could say is that if after, call it 10 years of these observations, you see nothing, then you're either going to have to fine-tune the potential to a degree that might be moderately uncomfortable, or you'll have to think about something that isn't quite so standard. So this, not quite as confident, but there's certainly at least a possibility for this to be in a few years. Okay, well, great. What are the things that we're going to be able to learn from this? I mean, this is what we really want to know. Seeing the gravitational waves at all, of course, should be a Nobel Prize-winning discovery for someone. And nonetheless, we always press on. We'd like to know what else we can learn. So we'll put up now our open questions. Now, what I mean by with gravitational waves is I'm going to start listing a few things where they are open questions, they're big questions, that I think could be potentially resolved by observations of gravitational waves in various ways. Now, we've already listed a couple of them, and so we'll start discussing this, the ground-based, then the cosmic microwave background, and then some things about more fundamental GR. So the nature of very dense matter. The stuff inside neutron stars is a few times the density of an atomic nucleus, and in a particular sense, it is cold. This cannot be made in the laboratory. Nuclear physicists have, violent for them, discussions about the nature of the matter. Is it mainly neutrons? Is it quark matter? Is it hyperons? Is it condensates? Is it strange matter? We don't know. There's a limit to what we can do in the laboratory. Again, you wouldn't want to actually have a neutron star in your lab. So we actually have to make these distant observations of neutron stars. And it turns out that knowing how massive a neutron star can be, but much more particularly its radius, can be a very good hint. There have been attempts so far, of course, but all the information we have electromagnetically is dominated by systematic error. So we really do not have a reliable and precise measurement of the neutron star radius. There are X-ray missions that are planned or approved that should do a good job, but it turns out that looking at the gravitational waves of neutron stars as they spiral together will be a major clue. Another thing that we just mentioned is the early universe. So, do you see it? If you see it, what is the amplitude? These are the sorts of things that would be very interesting to cosmologists, to put it mildly. What about black holes and extreme gravity themselves? Yes?
What type of information about these waves is going to be measured? Frequency, amplitude, what else?
Polarization as well. So
only three factors will contain information to discriminate among different models?
They will, but remember that frequency has a lot of information to it. So one of the things I'm about to mention, for example, is if you have, say, two black holes spiraling into each other, are they spiraling in a quasi-circular orbit that's just gradually going in, or are they coming in with an eccentric orbit? You also, in the frequency, amplitude, and polarization information, have information about how the black holes spin and how they're oriented. So there's actually a considerable amount of info you can get out of this.
What determines the frequency? What's the main factor determining this frequency?
In these cases?
Yeah.
Okay, so these are technological and or reality-based limits. So if you talk about frequencies less than about 10 hertz on the ground, the shaking of the ground gives you a noise source that's very difficult to get around. If you talk about space-based, then if you have something of a certain size and many, many wavelengths fit in that size, it kind of self-cancels. So if you go to too high a frequency, you're not going to be able to see things with much sensitivity. If you go to too low a frequency, you start worrying about other things like the orbit itself giving you extra noise you wouldn't be able to see. For pulsars, the issue is that although theoretically you could imagine going up to a higher frequency, these things are many thousands of light years away. So you have lots and lots of cycles fitting in and self-canceling. This limit is because we have a finite amount of time. So 1 over this is about 3 years. So the longer we wait, the lower the frequency we can go. But maybe there are properties about pulsars themselves that make them timing in those long durations tough. For the CMB, this is related to a question we had earlier. If you go to a significantly higher frequency, you have what are called foreground sources. So say massive clusters of galaxies, which can introduce this particular type of polarization. And therefore, much as I like clusters of galaxies and I'm a big fan of matter and all that, it's not the same thing as having gravitational waves from the very early universe. Okay?
Might be the 1 over mass scaling too.
True. So
you might want to explain.
Good. So the other thing is, if we go all the way back here to our discussion of the radius as a function of mass, we find that for black holes, and this is unique to all other compared to all other objects, there is no actual mass scaling. So that is to say, if you think about, say, a star, for something to be a star, it has a range of masses that it can be in. So somewhere between about 1/10 of a solar mass and maybe 100 or so solar masses. For a black hole, in principle, if you were a sufficiently advanced alien and had a lot of spare time in your hands, you'd be able to construct a black hole of any mass at all. Now, this is where you get some of these different masses. The highest characteristic frequency that you can get goes like 1 divided by the mass. So that's one of the reasons why, if you're talking about somewhat higher frequencies here, you're only able to go up to maybe 10 to the 6 or 7 solar masses. The giants would be too low a frequency. Okay. So in terms of our open questions here, so these are a couple of aspects of astrophysics and cosmology you'll be able to lead to. Well, if you then ask, what are you going to learn about strong gravity? And this is one of the things I was trying to sell to you, the idea that black holes are extreme gravity, and so we press our knowledge of fundamental physics. You are going to learn a great deal. So in terms of fundamental gravity, polarization. So I was showing you how you have this sort of classic 2 modes of polarization for gravitational waves. But in alternate theories, you can have additional polarizations. So if we see additional polarizations in gravitational waves, this is going to be big news. It's something that would suggest a different type of theory than general relativity. The speed of gravitational waves. According to general relativity, it should be the speed of light. Well, there are events. For example, when 2 neutron stars spiral into each other, a lot of people, most probably, they think that this produces a category of gamma ray bursts. So very bright events, the so-called short, hard gamma ray bursts. And these are going to be able to give you a very precisely defined time in which the gamma rays were first emitted, and then you can compare that with the time of the gravitational waves. Now, there'd be some astrophysics about is there a delay of a little bit, but let's suppose that you're a millisecond or a second or something at most different, and you're talking about something that was emitted several 100 million years ago. So this is going to give you great precision about the relative speed. And then you have the waveform. So the waveform, if you like, is kind of the combination of the frequency, amplitude, and polarization as a function of time. So for example, if you have your binary, then it's coming in and initially far apart. It's not emitting a lot of gravitational waves. It's gradually spiraling in, and it goes faster and faster and faster. So you actually know what waveform to expect modulo some parameters. Now, I said very early on, this is actually helpful in detecting the sources to begin with. So as an example, some of you possibly have gone to wild parties, the kind of party where it's so loud that even talking to somebody right in front of you, you have to yell. Well, if you're a nerd like I am, you may have noticed that it's actually helpful in your conversation to look at the person speaking, even if you're not a lip reader. You get some sense of what they might be saying, and therefore you're able to drag some of the signal out of the noise. So not only is it helpful in detection, but the comparison of these waveforms with what we see is going to be an outstanding test of the principles of very strong gravity. So that's pretty good. However, most of the participants in the Universe of Black Holes workshop that's going on are astrophysicists. So although we certainly appreciate fundamental gravity, we'd like to know the role of black holes in the universe. And there are a variety of things that have been discovered. So just one of these. Let's suppose that we plot the mass of a black hole in the center of a galaxy of billions of stars versus the mass of the galaxy, which, astrophysicists, I'm using a shorthand for the bulge. If we were to do this, then we find that, stunningly, more massive galaxies have more massive black holes. This may not strike you as particularly interesting or surprising, but detailed analysis of this and many other pieces of information suggests that, as a matter of fact, the central black hole of the galaxy may have a key role to play in that galaxy's development. Now, why is that surprising? It's a size comparison. If you were to take, say, the black hole in the center of our galaxy and compare it with the size of our galaxy, it'd be like the comparison of a human egg cell with the Earth. So we've got something very small which is managing to have a pretty major influence on something that is very substantial indeed. Now, what else? I keep talking about these galaxies. There are billions of them in the universe, and they move around, and they're big enough that they do collide every now and then. For example, in 4 or 5 billion years, we, in our Milky Way, are going to collide with the nearest big galaxy, Andromeda. Now, if you do have black holes in the center, these spiral together, and eventually, maybe, are going to come together. It's tough to say for sure using electromagnetic observations only. And the reason is, again, the vastness of space. So we have some instruments out there that have unbelievable angular resolution. If you were to take the state-of-the-art, world-spanning radio telescope arrays, for example, you'd be able to resolve an angle, which is more or less the equivalent of being able to see a fly's egg in Los Angeles from here. So that's pretty impressive. But now, if you take the source and put it 1 billion light years away, suddenly you're talking about still several light years. So even if you could see black holes, and you usually don't at that separation, it's not absolutely sure that they're going to get together. They probably will. Yes?
So how do you know that it's the mass of the black hole which have an influence on the mass of the galaxy and on the other way around? So
this, as so many other things, is kind of a bit of indirect evidence. And it's not the mass of the black hole per se that has the influence. Remember I mentioned earlier that if you have gas spiraling around, it emits a gigantic amount of energy. That energy is believed to couple to gas in the galaxy, especially, to be able to influence it, to cause the galaxies to evolve the way they do after, say, a major collision of 2 roughly comparable mass galaxies. So I may have misled you. The mass of the black hole is so tiny that it's irrelevant. So from our standpoint, whether there's a black hole in the center of our galaxy or not, we'll orbit exactly the same. But it's the stuff spiraling in and blasting out amount of energy that seems to have the influence. Good. Okay. So in terms of these black holes spiraling in, all right, so maybe with gravitational waves, with these two, we'll be able to actually see the inspirals. In the space-based case, the actual inspiral. In the pulsar case, they'd be farther apart, so not quite ready to inspiral. But this gives us a huge amount of information. Why? Well, as I was saying earlier, with these space-based detectors, if you're actually able to see the final inspiral, you will be able to tell whether the orbit was circular or eccentric. You'll be able to tell how fast the black holes were spinning. Were they spinning parallel to each other in the orbit, or were they kind of oriented every which way? This has very important consequences in terms of the dynamics of the galaxy, the interaction of the galaxies with each other, of the black holes with each other, and with the gas. These are things we cannot resolve with electromagnetic observations. So this is going to be a key observation to make. Indeed, there's even an early portion of the universe, not quite as early as this, but when the universe was maybe 1% of its current age, which might be critically revealed by gravitational waves. So as it turns out, the universe back in the day of the microwave background was really smooth, a part in 10 to the 5 kind of variations in density. It's just incredibly smooth. Now it isn't. You and I are 10 to the 30th times denser than the universe on average. So there's a big role that has to be played by something to go from smooth to lumpy. Now we know a lot of that story, but the phase where the first stars, the first galaxies were formed is going to be very difficult to observe. There's good reason to think that with something like a space-based mission, it would be possible to see the black holes of those earliest galaxies merging with each other. So, in summary, we have increasingly recognized that black holes play a vital role in the universe, and the imminent era of gravitational wave detection will open up new windows in the many faces of black holes. So stay tuned. Thank you.
Questions?
I think there has been talk of using atomic physics to measure gravitational waves.
Yeah.
So can you speak a little bit about that and why or why not it would be useful?
So people have talked about atom interferometry, where you basically have atoms in free fall. And the consensus seems to be kind of swinging back and forth about whether this is something that's likely to be possible. The naysayers suggest that the requirements you have on the laser technology, which would have to be coupled to this, are at least as stringent as they would be for laser interferometers in this, so there's no real reason to go in that direction. I do not personally know, however, whether there is a reason to say this can be eliminated, we don't have to consider it at all, or whether it really is something that's worthwhile pursuing. The consensus seems to be kind of on the negative side of the moment.
Could you comment on one additional point? There's one row which is left off after CMB, which is actually detecting primordial gravitational waves, not necessarily just from inflation, but that's really going on inflation.
Yes.
And could you comment on the role of this VBO and similar missions? Okay.
So in terms of the primordial, there it's really going to be a question of, so you're talking about like from the Planck time. Yeah. So the BBO, the Big Bang Observatory, there's a suggestion, so this is beyond the space base, so I may need to freeze myself to see the BBO actually fly. And the thought is that if you look at the gravitational wave spectrum, a part that is not actually represented here, so somewhere between maybe 10 to the minus 2 and say 1 hertz, is going to be the cleanest portion of the spectrum for other sources, and therefore you might be able to look for weak but background sources like the primordial gravitational wave background. I think the problem is that so what you have to do is actually remove individual sources. So as double black holes and double neutron stars sweep through, you have to be able to identify them. And based on guesses about the amplitude, you'd have to be able to remove those foreground signals to a part in a billion or something in order to actually see them. So I'd love it, but I'm not all that optimistic.
Can you a little bit of like how by measuring the polarization by CMB you can deduce this black hole spiraling gravitational wave?
Yes. So the polarization is one aspect, and I'll get to it. But more generally, if you have, let's say, two black holes that are spiraling into each other, it undergoes what is usually called a chirp, because when they're far separated, the frequencies are low and the amplitude is low as a result. As they get closer, the frequency goes up, so does the amplitude. Now, in terms of the polarization, suppose that you have two black holes which are spinning in some sort of random direction and they get close. This can couple them and actually shift the orbital axis as well. This means that the ratio between the two different polarizations would change as a result. So some people have used that in a hopeful way as being able to break some of the degeneracy you have in interpreting parameters.
Are you suggesting that knowing the polarization speed and waveform of these waves will allow you to discriminate among different models of gravity in the end?
It's an interestingly tricky question. So if you have, let's suppose, and people have proposed these, suppose you have a model of gravity, an extra parameter x, such that x is 0 gives you general relativity, and x non-zero gives you something else. The best you'd, of course, ever be able to do is to be able to say that x is less than something if you have a certain amount of agreement. But part of the difficulty is waveforms, especially two black holes close to each other. It has taken a phenomenal numerical computers, millions of node hours, in order to be able to calculate these things and we hope compare them with data. So if you have a totally different theory, the question is, can you convince people to spend that kind of effort? What I suspect will happen is that if there is clearly a significant disagreement with the predictions of general relativity, people will try to gear up for that effort. Otherwise, it'll be a matter of constraining how far you can be from GR. There are people like Nico Yunus at Montana State who worked a lot on this.
Thanks, Paul.